So Curtis Judd did a video on the myths of 32-bit float, which I thought was great. Um, I've been trying to tell him for a couple of years that, 32-bit float doesn't make the gain knob obsolete. It doesn't fix clipping. And I thought, he'd gotten there. And so he did a video about the myths, which is a great video. It's all correct, and it was great practical advice. And so I was really happy because I was like, now I don't, there's a big YouTuber out there that's finally understands, and I don't have to do any videos about this stupid subject. And then he just did a video yesterday. He released Camera Bros Don't Hate Audio, where he backtracks, where he sort of says, yeah, you can use 32-bit float if you're busy and you don't want to deal with the gain knob, then yeah, 32-bit float can be used, but you really want to use the gain knob, so I don't think you should use it, but if you really want to, you can. And I think the reason that he did that is because, well, a couple of reasons. The small reason is that in the comments of that video where he talked about the myths, he got a lot of pushback from people saying, oh, it works, or they're just pushing back on it, like, works for me. And so then now he's sort of like, again, hedging his bets going back. I don't think, so it's not like as if he's done a bunch of tests and he said, oh, I think it works, and Max, you're wrong. It isn't about that at all. We can't even communicate in the same way. And I think with many people. So I'm going to take another approach here in this video to explain that this isn't really this isn't a technical issue so much as a psychological and experiential issue here of what's going on, about why he doesn't understand that 32-bit float doesn't, have anything to do with the gain knob or clipping. And I was thinking, okay, maybe I should just title this video in a sense like, Curtis, don't hate on us engineers, because that's a difference. See, he's never done any engineering. It's obvious to me. Like, he's never tried to build a microphone. He's never tried to build electronics. He's never tried to work on a car. Do you know what I'm saying? Like, he's never done actual engineering, either with computers or which are abstract, or with cars or stuff like that. So, when I was young, like a very early picture of me pulling apart tea bags, I took apart everything when I was a kid. Like, my father had a really nice, reel-to-reel tape deck. I took it completely apart. It never worked again. And of course, my father was extremely upset, but my parents were sort of like, he's ruining all this stuff, but he's learning. And I've always been that way, and Curtis has been a different way. It's not like one's better than the other. So anyway, so from an engineering point of view, the reason it's hard for him to see this is because he doesn't work with the materials. Like, he doesn't work with I'm going to go into some slides where I sort of explain this. But I want to go into another problem. The problem for me is, okay, so, my channel, I get many people saying, why your channel stinks, you're so obnoxious, you think you're right about everything. I'm like, I agree with you. I know I'm obnoxious. I don't mean to be obnoxious. So the problem is okay, so I want to talk about something, right? I want to say, okay, I want to talk about how microphones, how they're ultimately digitized, right? But who's interested in that? Are you interested in that? Is anybody who really picks up a camera interested in that? No, very few people are interested. So if I do this video and I say, okay, I want to talk about how audio is digitized, and I start going into all of it, everybody's going to fall asleep and not being interested, right? So how do you make it interesting to people? If I then say, okay, but then I challenge somebody, I say, well, it's not really quite how you understand it, right? Well, now people are getting defensive, right? So if I say, okay, well, X is wrong about this, and this is why, that gets people interested. But if they've already bought into it, right? If they've already bought a 32-bit float recorder, now it's emotional to them, so they don't want to get into it. So you're danged no matter which way you do. If you just talk about the technology, then nobody's interested except other people who sort of already see things the way you see them. So they just want to accelerate. So other engineers would look at it and be like, oh, okay, yeah, I see this better. You're talking my language. But if you're, trying to use the equipment, then you just start to get defensive. So then that doesn't work, right? But that you sort of need that to challenge the person to get them interested in a technical subject, right? So again, whichever way you do it, you don't do it. So that's why long ago on this channel, I've been like, I'm just going to be myself. And, I know that most people will not like the video, but for those few people, it will be like a home. Like, I'm not crazy. Like, yes, like all this marketing nonsense out there, like here, there's somebody that understands. All right. So I'm going to go into some videos about how electronics work. But actually, before I do that, I also wanted to maybe title this video, the problem with all this stuff is lack of rubber bands. So like I was looking for a rubber band to do this video all over. I can't find it. When I was a kid, rubber bands everywhere. So when you have a rubber band, you can explain this stuff with a rubber band. So I'm going to explain, like, pretend like I have a rubber band. So let's say you're a kid, right? And you have a rubber band. When I was a kid and I had a rubber band, right? If you pull it and you don't pull it enough, right? It doesn't go forward. It just falls down, right? So there's a certain amount where you pull and it doesn't really convert that pulling into forward motion, right? And then there's a certain amount where you pull it and it actually goes forward in a good way and you can aim it. So you can aim it pretty well, pull it back, you shoot it, pull it, you can aim it. But if you pull it back way too far and you try and aim it, you can't. It gets out of control, right? Or it breaks. And that is true for every single material on Earth. And so the problem in dealing with audio and everything is when you're an engineer, when you work with stuff, you realize every material has a non-linear reaction to force. A rubber band does not have, like if you measure the amount of force newtons or whatever, or that you're pulling back the rubber band and you put it on a scale and you say, okay, I pull it back 1, it goes 1 foot. I pull it back 2, it goes 2 feet. I pull it back 3, it goes 3 feet. It doesn't work that way. It'll work that way in a certain like center in an optimal range, but it doesn't work that way in the beginning and it doesn't work that way at the end. So it's usually like an S curve, you'll see, right? So everything doesn't have a nonlinear response. And because of that, with a microphone, because the range of a microphone voltage is so wide, right? It's so wide that you can only pick one part of it and then feed it through these materials to get the best nonlinear response, to get the most accurate representation of what's in the microphone. It's because it's so wide. And you can prove this to yourself by like if you're just talking, and Curtis mentions this in his like myths about 32-bit flow, right? He mentions like, hey, listen, if you're just talking, right, in your microphone and you don't try and set the gain too high, you're going to be fine. The audio will be as perfect as you could want it, which is correct. But from an engineer's point of view, what he's saying is that if you speak in a range, if you start with the source voltage that's in a small range, right, and it's not too low where you're getting a bunch of noise, right, then forget about the high end, about the clipping end. If you're above where you're getting noise and you're getting this small range, the materials will give you a linear response. In other words, good audio. So rubber bands, like you pull it too far, too back, you get bad aim. Too low, it doesn't really go forward in any sort of direction, right? That's noise. That the far thing is like clipping, right? So, but if you're in a good range, if you're always going to pull the rubber band at a certain range, you're going to get, you're going to hit what you want to hit, right? So, that's from an engineer's point of view. So I'm now going to go into these charts I did yesterday just to explain some of the history of this and how automatic gain control works. Like I said, so to make this video, now I'm not going to talk about like, oh, he's right, wrong, whatever, or I'm challenge you. I'm just going to tell you like, hey, listen, this stuff has been around for a long time, and I'll explain to you some of the history behind it. Is this working? I think it's working. All right, so we have a first slide. We have energy power we want to regulate. So think about, again, we're going to get back to the microphone, but I'm just going to start with this. And sorry, okay. So the So here's a governor and a throttle valve. Now, if you go to the Smithsonian Museum or anywhere like that, if you're an engineering type like me, these things are wicked fascinating. And so the way the governor works here, so I think you can see my my mouse. So as the engine is spinning, there are these balls, and as it spins, the balls go higher and higher. But then they reach such a point, as you can see, they're on these like pulleys, that they will pull down on this lever that pulls up over here, and will basically, there's a throttle valve that will throttle how much energy is going to the system. So if you're in a locomotive, or basically these are used in steam engines, so basically if you had a steam engine, you didn't want it to get so powerful that it would basically blow out the gears of whatever it was driving, right? So as more and more power came through the system, you want to say, okay, well, you reach this power, throttle it back, and that's how this works. And so here's another diagram of that. So you have this boiler, right? And the boiler's going into this engine, right? It's running the engine. And so as the engine goes, if the engine starts to go too fast, like on a train, like the train is going too fast, then as it spins this thing around, it will reach a point where, let's say 80 miles per hour or whatever, that it will basically throttle down the steam from the boiler to slow down the engine, so the engine would never go too fast. Similarly, if it's going too fast and then it starts, let's say it starts to go uphill, as it starts to go uphill, and the wheels are moving slower, it would then say, oh, give us more pressure from the steam engine. So that's how these early governors worked. So just you sort of keep that in mind, and they're just fascinating devices. And here's one, a real life one from a Corliss engine, I think. So yeah, it's just fascinating. Whoever thought up that idea, right? Let's see. Okay, and then here's somebody's steam engine, like they run at home, and here it is right here. Again, this will regulate the steam coming from the engine to drive all this, because if it drives too fast, right, this stuff will generate too much friction, and it might just fall apart or whatever. So you have that. These can also be used to regulate the pressure. This is a diode. So in electric circuits, when you send a voltage, you actually need a certain voltage before it'll start working. So even if you're going in the right direction here, right, and you're putting in the voltage, it won't actually send anything until it reaches the threshold. And that's sort of like I was explaining with the rubber band. Like the rubber band needs a certain amount of force before it actually go forward. So you're putting in this force, and now it's going forward, right? I'm sorry, you're putting in this force here, right? Now it's going forward. But then after you get too much, it just loses control. So basically this is, each one of these is sort of like noise at the high end, noise at the low end. But the basic thing is, again, the diode does not have a linear relationship like this, right? It's not a straight line up and down. So a diode is a good thing that really shows this non-linearity of all materials, or most materials, whatever. And then here, I asked Claude, so just talk about a resistor, which is, of course, the main thing that's used in a amplifier is a transistor, but a transistor, remember, it's a transference resistor. So a transistor is sort of like a resistor too. It's transient resistance, right? So as a current flows through a resistor, it heats up, which changes its resistance value. So it's the same thing with a microphone. So just think about this in a, exaggerated way. At the high end, if you're speaking with a microphone voltage that's so high, then it's going to start heating itself up, right? And as the heating changes, the resistance changes, right? The impedance changes. So that creates a nonlinearity. There's also the actually, first I think it's talking about the different temperatures. The temperature affects things. So a lot of electronics in preamps is not actually about the amplification of the microphone. It's actually about the temperature changes on the electronics to compensate for that. So you would get the same amplification if you're using your preamp, outside in 90-degree weather, or you're using it where it's 30 degrees weather, right? The components inside the electronics will behave differently. So they put in electronics to basically compensate for those different resistance levels, different circuit behaviors at different temperatures. So you have that. You have the power nonlinearity where it's creating heat. Here's and then here's frequency dependency. So the other thing is that at certain frequencies, you can start generating a magnetic field, which regenerates a current. So you have those issues. And then it explains current noise. At very low signals, current flowing through the resistor generates noise. So again, you all know what noise is, and it's sort of like the rubber band. When you don't give it quite enough, pressure pulling it back, it doesn't really go forward that much, and it goes in the wrong direction. So to think about the rubber band, like if you want to hit what you want to hit, you need a certain amount of pullback, right? Too little, you get noise. Too much, and you don't really hit your target, which is another sort of type of noise. All right. So, and then this, so here's a microphone. So we're going to tie this all into the governor. So an automatic gain control or limiters, this is how they work. You're sending your voltage from the microphone into your transistor right here. You have a large voltage coming down into the transistor. So let's just say it's 2 volts, right, or whatever. And remember, from the microphone, you're getting microvolts or millivolts, really small voltages. Anyway, so you have this voltage coming down, and how do you know if the microphone is too high, if you're about to clip? You don't actually know it by looking at the voltage from the microphone. You look at it by looking at the amplified voltage from the microphone. And so it's just like that steam engine. So you're looking at the current coming from essentially your wall or a battery into your preamp. This 1 volt, right? So it's coming down, and then it goes into like a governor thing. And the governor says, oh my God, you're maxed out at like 1 volt. So go back and reduce the voltage going into your transistor. And that's how it works, automatic gain control or limiters. So you don't need 32-bit float to do that. This technology has been around forever. It's an electronics principle, and you would do it on the electronics end. You would not do it. I mean, you can use it using digital signal processing with the data later on. You can, there are ways. It's very complicated that you can sort of do it, but really this is the best place to do it, because on the electronics end, from the microphone, from the voltage, once you've lost that voltage, you can't get it back. I mean, digital signal processing can't get it back. So the best way to reduce clipping is to have an automatic gain control or limiter circuit in the electronics of the preamp, not in the data side of the equation, 32-bit float, 24-bit, 16-bit, whatever, not in that part. Okay, I don't know if any of that meant sense to you. I'm very close to this closing down this channel because, again, I don't know. I mean, it's just I just get so many negative comments, and whatever I say, it's like Edward Scissorhands. Whatever I said, I'm annoying somebody, and I find this stuff very fascinating. I don't know. Anyway. So, again, the main thing is engineering is fun, but you have to get into it a little bit if you can understand these things. So as Curtis said, hey, camera guys, don't hate on audio. I say on both of you, camera guys and audio guys, don't hate on engineering. Go get an Arduino, a Raspberry Pi, an ESP32, go get some electronics, go to your local hackspace, do some electronics, build a microphone, go work on your car, go work on anything, go fix the toaster, right? When you work with materials in the real world, whether it's electronics or it's metal or plant, whatever, all these things the light bulb will go off in your head, and you'll be able to see how everything is sort of the same. The preamp is the same as a car. It's the same as a coffee maker in a sense. All these things, all mechanics are the same, whether it's electrical engineering, mechanical engineering. It's all sort of the same. That's why you'll know that most people that can do one thing generally can do them all, right? To some extent, right? But you're not going to understand that. If you want to understand how your equipment works, you need to go actually try and build it yourself. That's how you learn. You build a teeny little circuit, a teeny little amplifier. You build a microphone. You put all the components together. Once you do that, you then see like, wow, like I have to get everything just right. Like nothing behaves the way that I expected it to behave or I want to behave. How am I going to fix it, right? So yeah, don't hate on engineering. Get into engineering. Engineering is fun. It really is. But if you're not going to get into it, don't hate on me, okay? Don't hate on me, all right? See you later.